The cooling curve of pure nickel shows a characteristic arrest point. A similar cooling curve can also be observed for pure copper. However, the arrest point, and therefore the temperature plateau, at which copper solidifies, lies at clearly lower temperature. But how does a mix of nickel and copper behave? Consider a nickel and copper mix of 70 to 30 and a mix of 30 to 70. The cooling curves of the mix show that the mixes solidify in a temperature interval and not at a specific temperature. Accordingly, the cooling curves do not show any arrest points anymore, but flat areas, which are limited by the upper and lower inflection points. The upper inflection point denotes the start, and the lower inflection point denotes the end of the solidification phase. What causes this cooling behavior of the nickel-copper mix? The nickel molecules form the first nuclei just below 1453 degrees Celsius when the mix is cooled. However, the nuclei don't exist for long since the crystallization is disrupted by the copper molecules. The first nuclei remain stable only on further cooling. The first nickel-copper mix crystals are formed where the proportion of copper in these crystals is still very small. The rest of the molten mass is therefore enriched with copper. The solidification point of the rest of the molten mass therefore falls further. If the crystals are to grow further, the mix must be cooled further. This interplay ends only once the entire mix solidifies. This results in the typical progression of the cooling curve for the nickel-copper mix. If the arrest points of nickel and copper, as well as the inflection points of the various nickel-copper mixes, are plotted against the proportion of copper, we get the phase diagram for this mix. If we connect the upper and lower inflection points of the various mixes to each other, we get the liquidus or solidus lines respectively. The liquidus line separates the area of the liquid phase. The entire mix is liquid above this line. In contrast, the solidus line separates the solid phase. The mix is completely solidified below this line. The solidus and liquidus line surround a lenticular area. If the temperature of the mix is in the range, a mix of crystals is present in the molten material, whereby the proportion of crystals increases top to bottom. Therefore, the mix becomes more viscous, that is to say, slow-moving with a decreasing temperature. We also use this effect for various manufacturing processes.